My name is Usama Ahmed, and I'm here to present my paper, Mending of Spatio-Temporal Dependencies in Block Adjacency Matrix. So the author of paper are Usama Ahmed, Umar Abdul Jalil, Usman Azir, and Murtaza Taj. And are affiliated with LAMS and BNU. So first of all, what is spatio-temporal data? As we know, spatial means location-based information and temporal means information changing over time. So the overall spatial-temporal data depends on both spatial and temporal dimensions. As we can see in this picture, the blue and green dots represented nodes of the graphs, and the lines demonstrate their interconnectivity between these nodes. And each node has a data of temporal data of t length. So, what are the example of spatial temporal data? As we know, spatial temporal data is there in every aspect of life of our lives, like in weather forecasting, environmental monitoring, urban planning, agriculture, public health, renewable energy forecasting, financial analysis, and traffic flow predictions. So in learning of these spatial-temporal data mainly consist of two main building blocks. One is pre-processing, in which we extract the features from our raw data, and in deep neural network we basically extract uh, feature based we learn the distribution of these extracted features, and use them in our prediction or regression tasks. In overall, the neural network of these models based on two different types of networks. One is spatial modeling, and other is the temporal modeling. In spatial modeling, we use convolution neural networks and graph networks to model our topology of graph. And in temporal modeling, we use TCN and RNN and transformers to learn sequential data. So the sequence of these building blocks also vary. It depends on your complexity or your architecture of your problem. Like in this example, in this paper, Euler framework, they have used GNN before RNN, and they used RNN is there to model the temporal data, and GNN is used to uh, uh, determine the topology of the graph. Simple in similar example, uh, RNN is used before GCN and is used in traffic forecasting in regression problem, and different features has been accommodated also. In remote sensing application, in the land cover mapping, they have used CNN to model spatial and temporal dependencies. This problem is related to classification task. So in this paper, reference is available in this slide. Propose the concept of block adjacency matrix, and in which they have concatenated adjacency matrix of different time stamps and feature matrix, and they used graph neural networks to model both spatial and temporal dependencies. So what is the problem with the block adjacency matrix? First one, when we concatenate these subgraphs into hypergraphs or supergraphs, disconnection occur at that point. Then we have zero eigenvalues that is proportional to disconnected components. For example, if we are connecting three subgraphs, we will get three extra non-zero eigenvalues. What is the impact of these zero eigenvalues? It simply impact our spectral graph clusterings. It means they will impact our learning in graph neural networks. So what is the solution of this disconnection? In our work, we present that if we add learnable connection, we can remove these disconnection in our adjacency matrix. So we use transformer in corridor block for this purpose. So this is the our proposed architectural pipeline that mainly consists of feature extraction and then convert these images to into super pixels. And I will tell you later what is the significance of these super pixels, and extract rag and feature matrices from them, and then concatenate these images, features or rag at different timestamp to obtain block adjacency matrix. Then we use encoder block for to get modified adjacency matrix and graph neural networks to learn spatio-temporal dependency from these modified and feature matrices. So after encoding block, we get a asymmetric adjacency matrix. In images, we usually have a symmetric matrix or undirected graphs. So to accommodate to or tackle this problem, we decompose these matrix into two components. One is asymmetric and other is asymmetric. So our loss function consists of two parts. One is cross entropy loss and other is penalty term with adjacent asymmetric matrix. We are enforcing our model to uh, accommodate symmetry in its prediction or learnable connections. So we have evaluated or proposed methods on two different data sets, like in C2D2 and search wisdom. C2D2 is the remote sensing data set that mainly consists of four classes of three and consists of three different timestamps data. And search wisdom is our action classification data set that classified different action performed by a robotic arm in surgical operation or clinical data. So, graph in images. So, in this paper, we are describing graphs on images. So, if we make graphs on images of having high resolution, we will get computationally complex graphs that will hardly we can hardly process those graphs in our GPUs or in our hardware. So to accommodate this challenge, we simply uh, convert these data into superpixels and determine their adjacency matrix and features. We also accommodate PG16 features in the matrix of feature. So we evaluated the evaluation metrics are sparsity and smoothness along with the accuracy. So sparsity determines how many number connections your transformer encoder block has added in your block adjacency matrix, and in sparsity is the how much quality quality of connection have been introduced in your uh, matrix. So these are the matrices of modified matrices on C2D2 that is evaluated on different settings of parameters like in L2 norm, L1 norm, and different penalty terms. As we can see, in L2 norm, we get relatively higher number of connections in comparison to L1 norm. So what are the interpretation of these connections? In left side shows the removal of disconnection or zero eigenvalues in modified block density matrix, and in right image indicates the Fiedler values of the uh, or Laplacian matrix after or before encoding. As we can see, the Fiedler values are non-zero after encoding. So we compare our results with other models. As we can see in this table, the performance is relatively high uh, on in comparison to other methods, but we get usually a high parameter number of parameters in comparison to stack GNN because they are using only graph networks, and we are using transformer encoders to modify those connections. Other methods can be applied so that we can get learnable or modified connections. But overall performance is better than he did ResNet. Ablative study, in this table we compare the sparsity, smoothness, and accuracy uh, quantitatively, and we can visualize that if for a certain number of smoothness and sparsity we get relatively higher accuracy. So these are our reference papers we have mentioned in our manuscript, and thank you for hearing me.